Recently, lightweight, high-strength carbon fiber reinforced polymer and glass fiber reinforced polymer composites have been increasingly used in high-performance applications. However, the production of carbon fibers has high energy costs and negative environmental impacts. Increasing demand for environmentally friendly products has made bamboo fiber reinforced polymers, or BFRP, a potentially attractive alternative. We aim to achieve better properties through a woven BFRP, whereas most research to date has used randomly oriented fibers.
We aim to design a weave of bamboo embedded in epoxy, so we decided to make a unit cell model to aid in our design. We generated a geometric model of a weave composite using TextGen, a third-party software. The TextGen model was imported into ANSYS, an engineering simulation software where a simulation of a tensile test was run. This test was a finite element analysis, where the model was composed of a finite number of elements and subsequent nodes, and each one was subjected to the applied simulation. The model was constrained to validate physical values by using periodic boundary conditions. The boundary conditions applied also allowed for the representation of a full sheet of weave by constraining each face to have equal values to the opposite side, so they may be repeated. This is a simulation of the tensile test performed. Notice the higher stress intensity within the fibers as well as the circular stress intensities arising on the closest face. The circular stress intensities represent where a transverse fiber is running over a longitudinal fiber subjected to the tensile stress.
We chose to harvest bamboo locally because it was more feasible than obtaining it from a distributor. We then cut each stalk before and after each node, as well as split the cylindrical bamboo into flatter segments in order for it to fit properly into a roller mill. Afterwards, we soaked the reduced segments in 0.1 molar sodium hydroxide to aid in the delignification of our bamboo. We used a chemical treatment due to time concerns, although we would ultimately want to soak it in just water to make our project environmentally friendly and greener. The segments were then washed with water to remove any remaining sodium hydroxide.
The delignified segments were dried at 120 degrees Celsius for 3 hours so that we could then extract the fibers. This process is important to ensure that all the water is removed from the fibers, preventing reduction in mechanical properties. We used a roller mill from the Aerospace Engineering Department's manufacturing building in order to separate the fibers from the bamboo. We did this by running through the pieces of bamboo through the roller mill and decreasing gap heights until the fibers began to separate. After they were crushed by the roller mill, the fibers were further separated manually into single fibers. In previous studies, smaller fiber diameter sizes have shown better mechanical properties, so we aim to obtain as small fibers as possible. The fibers were then organized according to length, so that we could more easily weave them on our loom. We grouped them into bundles of 8 to be woven into the mat, and then wove them into several bamboo fiber mats.
The weave was then inserted into a 3D printed mold filled with epoxy and allowed to cure for 24 hours. We made similar samples using a carbon fiber weave as well as just epoxy for comparison of the mechanical properties. These images show the completed samples that were ready to be tested.
We had to spray paint our samples white and then speckle them with a black spray paint, so that way when we did the digital image correlation to measure the strain rate throughout our samples, the camera could pick up the distance between each speckle and then model the strain throughout the sample. We tensile tested our samples at the Army Research Lab on Aberdeen Proving Grounds with an Inistron tensile testing machine. A high-speed camera was used to image the spectral pattern, which allowed us to generate our strain maps of our samples. Unfortunately, our BFRP samples exhibited lower than expected strengths. This was probably due to the small fiber fraction in our samples and the utilization of a single layer of bamboo fiber weave. This could also be attributed to the fact that the epoxy we used was designed for adhesion with carbon fiber. Ultimately, in future work, we would use epoxy CY230 and hardener HY951 to obtain better adhesion with our bamboo fibers.